In this section, we're going to look at weak bases, and the two types of weak bases are bases that come from neutrally charged molecules, so such as ammonia and ammonia derivatives. Okay. Or weak bases can come from anions, so anions that have the ability to receive a proton from another species, typically from water. So two types, neutrally charged molecules or anions that can receive a proton. So if we look at the first one right here, the reaction of C4H9NH2 with water, okay, we can see that that is a neutrally charged molecule. It's going to react with water, and in doing so, it's going to absorb a proton from water. So C4H9NH3 positive plus OH negative. And so as we can see here, it's generating hydroxide, which makes it a base. We know that the H has to go on to the NH2 portion because the H cannot be absorbed onto this portion of the molecule. Otherwise, carbon would be fulfilling its bonding capacity and would not be able to bond to the nitrogen. So the H would have to bond onto this portion of the molecule. And then you end up with, as I said, hydroxide. So in this case, the equilibrium law, note that the subscript is Kb because this is an equilibrium law involving hydroxide. We have hydroxide, concentration of hydroxide at equilibrium, concentration of C4H9NH3 positive at equilibrium, all over your concentration of C4H9NH2 at equilibrium. In the case of an anion that is absorbing a proton from water, we have right here the hypochlorite ion. So we'll take a look. We have OCl minus plus H2O, double arrow. The water is going to donate a proton to the OCl minus, and then we get HOCl, which is its conjugate acid, plus OH minus. Again, generating hydroxide, therefore this is a base. Our Kb for this, our Kb equilibrium law is HOCl at equilibrium concentration times the OH minus equilibrium concentration all over the hypochlorite concentration at equilibrium. Again, these are weak bases, so for any weak base, only a fraction of the weak base results in the formation of OH minus. So because we're using equilibrium expressions, we know that these reactions do not go to completion, they set up an equilibrium with water. So example 1. What is the pH of a 0.3 morphine solution if the Kb of morphine is 7.5 times 10 to the negative 7? So again, these calculations are going to be similar to the ones that we did with weak acids because they exist in equilibrium with water. So I'll start with my chemical equation. So C17H19NO3 is going to react with water by absorbing a proton. And we end up with OH minus plus C17H19NO3, and we'll just put H plus on the end right there. We make our ice chart, and then we input the lines for water because it is a liquid, pure liquid, so its concentration is density and therefore a constant. We input our initial value of our initial concentration of the morphine solution. We have no concentration of these two species, so we know that the equilibrium is going to shift right. Plus X, minus X, and then at equilibrium, we're at my equilibrium law, which is OH minus C17H19NO3H plus all over the equilibrium concentration of the morphine. Okay. And now I'll insert my value. So I have the Kb of morphine given to me in the question. I have 7.5 times 10 to the negative 7. And then my equilibrium concentration of hydroxide is X multiplied by the equilibrium concentration of the conjugate acid of morphine, right? The conjugate acid of morphine, that's also X. So X times X, that's going to be X squared all over 0.300 minus X. If I go to check my 100 rule, it will check out because my Kb value is very small and my initial concentration relative to the Kb value is quite large. So my Kb, or rather my 100 rule is going to work out here. So I can just assume, and so I'll write what I'm going to assume. I'm going to assume that 0.300 minus X is just approximately equal to 0.300 because this X value will be exceedingly small and will not affect 0.300 when we subtract it. So therefore, 7.5 times 10 to the negative 7 is basically just equal to X squared over 0.3. When I go to isolate X, so I'm going to get two values, right, because I'm going to take the square root of both sides, but I'm only going to take the positive value because the negative value does not make sense in this context. So my X is approximately equal to 4.74 times 10 to the negative 4. So 4.74 times 10 to the negative 4. And as we know, that is our equilibrium concentration of hydroxide. Once we have the equilibrium concentration of hydroxide, we can perform a pOH calculation, which is negative log of your OH minus. So in this case, it's negative log of 4.74 times 10 to the negative 4. And my pOH is equal to 3.32. The question, let's say approximately. The question did not ask for the pOH, it asked for the pH, but I know that I can get pH from doing this calculation, 14 minus pOH. So that's equal to 14 minus 3.32, and that will be approximately equal to 10.7. And I use approximately because there was a lot of approximations going on in the previous, throughout the previous question, right? So even over here, after I made my assumption, I had to do an approximation. Then I got an approximation here, another approximation here, so on and so forth. So the pH value of this solution is going to be 10.7. As we can see, that's a weak base because it's not a particularly high pH. And not all of the morphine, right, will react fully to produce hydroxide, right? It exists in equilibrium with water to produce hydroxide. Okay, what concentration of methylamine, which is CH3NH2, and the Kb values given, will give a pH of 11.5? So in this case right here, I have a neutrally charged molecule reacting with water to give me a pH of 11.5, but I do not have the initial concentration. So this is very similar to one of the questions that we did with the weak acid, in which we do not have the initial concentration, so we list it as Y. I'm going to start off by writing the equilibrium expression. Again, water is going to donate its proton, and I do not have this initial concentration, so I put that down as Y. I know initially I don't have any of these present. It will shift right to produce them, and at equilibrium I have X and I have X. And then I have minus X, so I have Y minus X. All right. I'm going to set up my Kb equation, which is equal to the concentration of OH minus at equilibrium CH3 NH3 positive all over CH3. NH2. The problem with this right now is that I do not have a value for either X or Y. But if I look at the equation, I have a pH of 11.5. So what I'm going to do is I'm going to find the pOH, and that's equal to 14 minus the pH. So I know that the pOH will be 14 minus 11.5, which is equal to 2.5. Once I have the pH, I can find the equilibrium concentration of OH, right? The equilibrium concentration of OH by doing 10 to the negative pOH. So 10 to the negative, in this case I've got 2.5. So what I can say here is, therefore, the concentration of OH minus at equilibrium is equal to 0.00316 molar, and recall that this is equal to X. Now that I have my X value here, 0.00316, I can just go and I can calculate. I know that my KB is, so therefore, I'm just going to take this basically and come up here. 4.4 times 10 to the negative 4, that's my KB value, is equal to the concentration of my X's. So I'll say X times X all over equilibrium concentration Y minus X. Okay, so I know what my X value is. It's 0.00316. So 0.00316, it's going to get squared because I'm multiplying it by itself, over Y minus 0.00316. Okay, so I'm going to do a fair amount of rearranging here and isolating of Y. So therefore, Y is equal to 0.0259. Okay, just by rearranging that. And that's molar. So the initial concentration of the methylamine here, right, my initial concentration was 0.0258 or 0.0259 molar. Okay, the relationship between Ka and Kb. So if we consider a generic acid and its conjugate base, A minus, or a base and its conjugate acid, HA, well, let's just take a look at HA and react it with water. So HA plus water, remember that the H will be donated, okay, and we end up with A minus plus H3O plus. Okay. If we looked at the A minus, so its conjugate base, if we looked at its reaction with water, it would be kind of the opposite. It would absorb an H, and we would have HA plus OH minus. So if I was to write a Ka for this equilibrium expression, so K sub A, because this is an acid equilibrium expression, I would have A minus at equilibrium times H3O plus at equilibrium all over concentration of HA at equilibrium. Same thing with Kb. I'm going to write an equilibrium law for this, so Kb is equal to HA at equilibrium, OH minus at equilibrium, all over A minus. So what I'll do now is I will multiply the Ka of this times the Kb of the conjugate base. So the Ka of the acid and Kb of the conjugate base. So Ka times Kb is equal to, and so I'll just write this out, A minus H3O plus all over HA, that's my Ka, and And then KB is HA OH minus all over A minus. And if I take a look at these fractions that are being multiplied, I've got HA in the denominator and HA in the numerator, and A minus in the numerator and A minus in the denominator. So they will cancel out, and I will end up with KA times KB is equal to H3O plus times OH minus. But we've seen this before. H3O plus times OH minus is actually equal to the KW of water, right? So this is the equilibrium expression for the autoionization of water, and that's equal to 10 to the negative 14. So H3O plus times 10 to the, times OH minus is equal to KW. So KA times KB is equal to 10 to the negative 14, which is KW, right there. Okay. So my conclusion is, if we flip to the next page, in general, for any conjugate acid-base pair, Ka times Kb is equal to 10 to the negative 14. So if I need to find a Kb, I'll basically take 10 to the negative 14, or Kw, and divide it by Ka. Okay. Or if I need to find Ka, I can do 10 to the negative 14 over Kb. However, this is the equation that you'll be using most often because Ka tables are plentiful. So there are a lot of Ka values given, and essentially what is assumed is that if you have the Ka, then you can find the Kb value of its conjugate base, right? So, for example, there is no table that gives us the Kb value of OCl minus, or the hypochlorite ion, right? What we have to do is we have to take the Ka and then use it to calculate Kb. So let's just quickly write that out so that you have that in your notes. So we do not have Kb for OCl minus in our table, but we have the Ka value for its conjugate acid, which is HOCl, right? Which is the conjugate acid of OCl minus. So because I have the Ka value for HOCl, I can use this equation to find the Kb value. So Kb is going to be equal to 10 to the negative 14, which is your Kw value, right? All over the Ka for HOCl, right? So the Kb of OCl minus is just 10 to the negative 14 over the Ka of the conjugate acid. So Kb of OCl minus is equal to 10 to the negative 14. And if I look up the Ka value for HOCl on the table, I get 4 times 10 to the negative 8. And so my Kb value is approximately equal to 2.5 times 10 to the negative 7. So whenever you're doing base calculations or calculations involving weak bases, you may initially need to find Kb value. So what I'm going to do right here is I'll put a little star so you can remind yourself, okay? When performing a weak base calculation, you may need to first calculate KB using the Ka of its conjugate acid. Okay, I'm going to put double stars there because that is often a sticking point for students, and they'll be trying to do a question on a test, and they will, raise their hand and ask, well, I can't do this calculation unless you give me the Kb value. I don't have the K value for this expression. And unfortunately, I can't help you in that situation because you should know that, okay, well, this is a weak base calculation, so therefore I need to first calculate the K by using the Ka value of its conjugate acid. Okay, the homework is listed below here. Thank you for watching.